Um,
Well,
so,
looks like no one else will join, and that's okay. So, where did we leave off? I was just starting to talk about iterators. First of all, is there anything that you'd like to ask me about last time? Or about anything else? Last time we did, what was it? That we just did peak. But it was sort of tricky.
iterate. If I understood correctly, iterators is just practically speaking an implementation of a method, right? So it just shows you the next uh, object if available within a certain data structure.
Yeah, so, yeah, I was actually
Yeah.
asking if you had any questions about the previous
Oh,
subject as well. But yeah, we can go on with iterators. Do you have any, though?
uh, honestly, no
Okay,
comments.
cool.
Like,
Yeah, yeah. I mean, it's tricky. But yeah, yeah. So iterators, yeah. So like the general concept of just implementing functionality that someone else named is a trait in Rust, but iterators are a very common example. So yeah, our first attempt will just be what are we doing here? Well, our first attempt will just be like the minimum viable thing we need to be able to iterate over a list, to be able to do this sort of thing, right? Um, and I guess actually maybe I can show her. Does she have testing code? Oh, she has. Her testing code is whatever, but it's not very like motivated. It just sort of looks like, um, it's like this is a way you can use iterator, but no one's really excited by doing next all on their own. Let me think if there's a better. Um, I'll just briefly do like a new test into iter for loop. So what we want to be able to do is we can copy this. And we want to be able to do for x in list. Let's actually make it really simple and let's make um, all of these pick a number. So let's just make it all the same number, and then I'm going to assert that they all equal that number.
great.
3. Okay, yeah. Um, so then I'm going to assert that x always equals 3. And this is going to yell at me. Do you know why this is going to yell at me, at least in general?
Uh, Probably because the iterator method is not yet implemented.
Yes.
So
Yes.
yeah.
The this thing is not an iterator. So it would need to be, well, what is this? Required for, huh. So there's this other trait into iterator that we might get into. I might talk about that a little bit because it is important. But I think the way that she's doing it is actually that we'll create a new type into iter that will actually be our iterator. So in the end, this code will work and this code will work. Um,
Mhm.
and
Uh,
we will
w-
create this. Yeah,
One quick question.
yeah,
So in the previous code, I saw that the this hash test, right?
yeah,
So
yeah,
it's
yeah.
a decorator, but how does Rust handles it?
This is a good question. I'm not gonna get too far into this, but I will talk about it briefly. I wish I had. It's a macro. Oh, and it's a compiler built in. Okay, but it's a macro, and macros are like preprocessors for your code. So you've written some C, right? With like hash define. You're vaguely familiar with that.
Yeah.
Yeah. So the way C works is you have like hash define macro 5 or whatever, and then later you're like printf %d macro, and there are two hang on. There are two phases here. Are you familiar with these two phases? Maybe not.
I didn't think it. I
Yeah.
don't think so.
So there are two phases, and they're kind of hidden from you. The compiler, importantly, like if we're being really particular about it, the compiler is a program that just understands C syntax. And the compiler never sees anything that starts with a hash or this A macro. What happens first is it goes through the preprocessor, which is shared between C and a bunch of other languages. And then it goes into the compiler itself. And then more stuff happens, but that's not important. So the preprocessor will look at this code and it will strip out hash define. It'll also strip out like hash include and replace hash include with like the contents of the file that we're including. But for hash defines, it'll just strip them out. But then anytime it sees the token A macro, so it's a little bit more than just seeing the text A macro. Like, I think if I put just A macro in the middle of a string, the preprocessor would be smart enough not to substitute that. But when it sees this, it replaces it with 5. And then when it gives it to the C compiler itself, the C compiler doesn't see this line, and it just sees like this printf line, but it says 5 here. Does that make sense?
Oh, I see. Yeah.
So this is a really clean separation in some sense. Like, it's really nice to implement it this way, especially if you're constrained in terms of like how many programs you want to write and you want to keep it simple. But it also sucks. Can you think of a way in which this might suck? Maybe it's not obvious here, but
maybe common definition or macroses within different files, and if they get united and they have different, not united, but like included, I guess. And if they have different value with conflict.
Right. So there might be a value conflict. That is very true. I think maybe a better example actually is something a tiny bit more complicated. Again, I said I wouldn't spend much time here, but I forget if this is the syntax for it. Let me look it up. C macro syntax. So I just want to see the syntax of, not that, function like macros. Okay, yeah, classic. This is not really something we use macros for these days, but it's a good simple example. And we don't use it for macros these days because the C compiler is actually smart enough to do what we're trying to do here. But we're trying to make a macro that calculates the minimum of two things. And this is what's called a function-like macro because it looks kind of like a function. And then we could do something like printf min of 5 and 6, or anything else, right? And in this case, this is going to turn into this, but with 5 substituted for A and 6 substituted for B. Mm-hmm. So post preprocessing, this will be something like, this will be something like, so many parentheses. Okay, like 5 is less than 6. and if that's true, 5, otherwise 6. And then ideally our compiler in this case is smart enough to just figure out that this is 5, right? But I don't know if I got the right number of parentheses. I think I didn't. Yeah.
Is there any advantages of actually? Yeah.
Yeah, go ahead.
Is there any advantage of doing this inline instead of making it as a macro instead of defining a new function? Like,
right.
If there is one less thing in the symbol table, does it matter?
It's not really about the symbol table. It is about the fact that that's a very good point. So the reason why we never use macros, even in C, for this purpose is, I guess it's twofold, but the primary reason is because there used to be a reason to do macros instead of new functions, and it no longer exists. It used to be that our compilers were really stupid, and whenever you define a new function, they would define that function, and then everywhere you called it, they would literally emit code to call that function, like as though they didn't know the definition of that function. But very quickly, they got smarter, and they do something called inlining now, where if you defined a min function, it would still create that function in the actual executable code, but if you then called it somewhere else in the same .c file, or even in some cases in different .c files, but if you call it somewhere else in your code, the compiler has a good chance of knowing what you're doing and inlining it. Meaning it says, okay, it would be stupid to pay the overhead of calling this and then returning from it. Because that's actually kind of expensive. The instructions, like you have to jump to a different instruction and weird stuff like that. It's just sort of needless for a function that's this small. But instead, the compiler can be like, okay, no, I actually know the definition of this function. I'm going to safely inline it, which means in the function I'm currently writing, I'm just going to copy that function's code, like the min function's code, and put it here. And then I'm going to do more optimizations on that inline thing, which is where the real benefit comes. Because in this particular case, if this were a function, and our compiler was not doing any inlining, because our compiler doesn't know the definition of min, say, right? Then our compiler has to do the call, and then at runtime, it's going to do the call, and it's going to do all the math, right? In this case, that's very short, but maybe this gets called a bunch of times, right?
Mm-hmm.
But if our compiler inlines it, and it's still a function in this case. Let's say our compiler inlines it, and it's a function. Then the compiler will, know what it means, and then it can do more optimizations. In this case, it can do an optimization called constant propagation, which is where it says, oh, I know what 5 is, I know what A is, it's 5, I know what B is, it's 6. I can actually do all this math at compile time and just replace the entire function call with the value 5, right? Which is nice in this case, but I mean, this is silly code, right? Very few people are actually writing this code and wanting it to be fast. But in the old days, before our compilers were smart enough to do that, the thing we wanted to do was to take advantage of all of that without inlining. So macros were basically like a manual inline. We would just write... we would tell the C preprocessor is way simpler, and literally the C preprocessor's job in some sense is to do the inlining, right? It just takes this thing and replaces it with this thing, and then when the compiler sees it, it just sees this really weird code, and then it can see all this code at once. It doesn't even know that it was once called min, and it can do whatever optimizations it can. And maybe if our compiler is dumb about inlining but smart about other things, even in this case, it could see, oh, this is always going to be 5, right? So these days, though, you should even if you're writing C, you should definitely be using functions, because the compiler will figure it out. But this is a good example because there are other problems with macros, or I guess the problem with macros, the reason... in some sense, the reason why we were motivated to make inline functions, well, a reason why we were motivated to make inline functions is that this is dangerous, because you might have noticed that there's lots of parentheses here, right? And those parentheses are actually there for a reason. They're here because a and b don't have to be integers. They could be expressions. So I could have written something like 5 plus 8, comma 6. And then the code that would result would actually be this. 5 plus 8 would get copied in a bunch of places, right? For every place that a was placed. And this is fine in this case, because I think less than has lower precedence than plus. But if we didn't have these parentheses, then it would actually have turned into like this.
Okay, yeah.
And you can see how errors can happen with, like, if we had, if this wasn't less than, but it was multiplication or something like that. And then it would bind to the 8, you know? Another big issue is, what if I had actually done, foo of 5 here. So foo is actually a function here, right? Well, the macro gets expanded, and we actually call foo twice. What if foo has a side effect? So, like, we wrote this code. It looks like we're calling foo once, but because it's a macro, it gets expanded, and in the expansion, we call foo of 5, and if that's less than 6, then we run foo of 5 again. So if foo is a funny little function, then we've really done weird stuff, right? So this is why we do inlining. I'm kind of losing the plot, but the point is, macros are still really useful because it's not just as a way of replacing functions. I don't have a good example. Test is kind of a bad example because it's so built into the compiler. But macros can do arbitrary code transformation. They can just take this code and like turn it into anything else that the compiler can figure out, like based on whatever rules. Maybe I've decided, oh, it would be... Maybe this is a way to reduce boilerplate. Maybe we have a bunch of boilerplate that exists for good reasons for the compiler's purposes, but then when the user's actually writing the code, they just want to be like, make this the I don't know, function, make this the function that runs when someone, actually, this is a good example. Yeah, I think, no, what's the super expressive Rust web framework?
Huh?
What the hell? I don't know. I do think it is Warp, though. Warp Rust. I think I just want to show a code example, because I think it's cool. No, that's not... Where's the... Warp? That's a terminal. Was it like Rocket Rust? Yeah, it was the Rocket Web Framework. It was this thing. They're all like boilerplate free. And this is how you write your code. This is an API route that takes a name and an age. And actually everything about like what the route is, like when this function gets called, is done in this macro. So this is one of the benefits of macros. This code, you know, you can think of the macro as just being a function that operates on this code, right? Which is complicated, but that it transforms this into something that actually has this function, but actually registers it as something that will run when the user does a GET request on a path of this form. Does that make sense?
Yeah.
Okay. So this can be powerful, but I just got done telling you how C macros are really, really scary because of things like this, right? Rust macros are better. I don't know if they're better in this particular way. It could still duplicate your code if you write the macro funny, but they are better in that they definitely avoid like conflicting definitions more. So you can name your macro something, and then like in the definition of your macro, okay, here's a good example. If I have this hash define A and B, min of A and B, In C, I definitely think it's a problem if I then pass a to this, right? Like if I have a different variable a, or I'm doing it wrong, but if I have it, whoops, if I do this, right? I don't know what C does here, because I gave it, like if I have an int a equal 5, you know, I shouldn't have changed the meaning of the code, but now like C has to, like the preprocessor has to deal with the fact that a is substituted for a, or I don't know, it just gets weird. Maybe actually this is fine. Huh. No, this is fine. Whatever. There can be conflicts, right? If I'm using this in a context. Oh no, here's a better example. This is the last macro thing I'm going to talk about, because then I want to talk about iterators for at least a little bit. Foo of a, no, foo of x int a equals 5. You can't do a return. How do you even... I don't even know how to write macros at this point. What do you do? I have a block. There's some magic to this. Because there's... I'm trying to figure... Okay, so they can do it with that, but that's all expressions. But then... Okay. What?
Huh.
Somehow this works. We have parentheses around this. We create
Around
these,
the block.
Around this block, and I don't know what... Oh. I guess this evaluates to this last expression. That's what makes sense to me. But anyway, you can already see that this is evil, right? This is how C macros get evil. What the heck? I mean, sure. But I just want... Okay. C macros get evil because we're using parentheses around this block because what we want is it to evaluate to this. And you can also see we're defining these variables with underscores because we don't want to conflict with other variable definitions. That's one of the things that Rust's system works to avoid. Rust's macro system is less cleanly separated. The compiler handles macros itself. But avoids shenanigans because it is smarter than simple text replacement. It always knows the whole language, right? So it is able to rename things dynamically so we don't have to worry about collisions. Because the problem with this macro is that if we actually had a variable named underscore a, this could potentially conflict with it. I don't think it would because we're in a new block. But no, it could conflict with it because if we then passed underscore a into int max, then it would try to refer to a variable it was declaring, right?
Yeah.
Yeah. So that sort of thing can't happen with Rust, and that's why their fancier macro system exists and why it's better. This macro system is not an invention of Rust's. Not really. Fancy macro systems are more associated with Lisp, honestly, and a couple of other languages have it as well. I think the term to Google for is like hygienic macros. because they practice good hygiene when it comes to identifiers and things like that. But yeah, so that was cool. I assume I answered your question and then some, or tried at least.
Definitely. And
Okay.
you know, I asked because I was looking at it. I was like, hey, a Python decorator,
Right,
right
right.
there.
Yeah, so it's not in some ways I prefer decorators because I think they're a simpler mental model because they operate more like, if I understand it correctly, when you have like an at decorator on something, um, that operates on the function. Like that thing might take the function as a parameter and then just transform it into a different function. But the macros actually, even though they are smarter than text replacement, they operate at the source code level. So like, uh, if I go to the println macro, maybe no, println's going to be built into. Maybe assert eq is not. Yeah, this is this is a macro. Everything that ends in an exclamation mark or has that hash is usually a macro. I'm not. This might be, but maybe it's built in. I think it's more built in because it's config. But this is definitely a macro, and anything that ends in an exclamation mark is a macro. And
Mhm.
this is operated like this is Rust code that processes Rust code. It takes two expressions, one of them named left, one of them named right, and then it turns it into. It evaluate. I don't even know what's going on here, but like I guess it evaluates to it. It evaluates the expressions. It figures out if they equal each other. I guess it took the reference to them and then it's dereferencing them for some reason. Maybe that's how it evaluates. I assume that does something useful. And then it calls this assert failed function. I think it's a function because it doesn't end an exclamation mark, but also my jump to definition is failing, so I don't know. With a kind, so like this, I guess this will run if it fails. I don't know. I don't understand most of this, but you can tell that it's actually operating on the code. Like we are able to deal with the things that we were passed as pieces of code. I think I've written a
Mhm.
macro somewhere. I could bring it up at some other point, but I want to go into just a little bit of iterators.
Oh.
Okay, so we want this code to work. So what do we have to do to get that code to work? Thank you for asking, though. This is way more interesting than just me talking about exactly what I have planned.
No, no problem.
So we want to implement this, and she has us make a new struct, which kind of makes sense because even for this dumb iterator, our iterator is logically a different thing from the list itself. So did I? I don't think I did. I don't think I did create this. So I'll just say pub struct into iter of type t. I should always capitalize these, but I don't actually. Oh, okay. And she's doing a little bit of funny syntax here, but I will explain that in a second. This is pretty straightforward. I'm just going to copy this. This is a new method on list that is going to be what creates the iterator.
Mhm.
So if I save this, I think so far, this now no longer has red squigglies because this is just creating an intuiter out of the list.
Mhm.
Now we have an interesting thing. Okay, we never read this field, so that's kind of nice. What's going on here? This is a new syntax that we haven't covered so far, I think, called a tuple struct. Basically, it's like, what if we use the syntax of a tuple to describe the members of our struct? So normally structs have named fields, right?
Mhm.
But for tuple structs, they don't have named fields, they have numbered fields. This warning is actually telling us about it. This has a numbered field 0. So if I have an instance of an intuiter, I can actually access its .0 field, which is the list inside of it. So this is mostly just shorthand because it's faster to write than having to give this a name. And there wouldn't really be a meaningful name anyway. And then it also means we create it in a different way. We just pass it in parentheses, like we're calling a function. But yeah, that's not that important. Then we do get to this, which is more interesting. I will copy it out, but then I'll explain it. Okay, so already we have fancy stuff. We're implementing with the parameter t, the trait iterator for into_iter of t. So this is the right thing to do, right? We're trying to make this an iterator. And then we're implementing the only method we have to implement, which is next, which takes a mutable reference to self, because iterators, when you call next on them, modify the iterator itself, which kind of makes sense, because the iterator keeps track of where it is. This is a mutating thing. And it gives us an option of capital self, which is another way of just saying into iter, or I guess in this context, into iter of t. It gives us an option of self : item, which means it gives us an option of this type. So this, we've already seen the type keyword used here, right? Where we were just giving a new name to this. Does that make sense? Do you remember that?
Mm-hmm.
Yeah. This is actually fancier. This is an associated type. So it says define an alias for an existing type, and it doesn't create a new type. But actually, this is an associated type, which is described down here with the example of iterator, which is great. And the reason for that is that iterator actually, the trait defines this type, but it doesn't set it equal to anything. So it says, in order to implement iterator, you must also define a type item to be a certain type. So this means that we can do things like, if we wanted to, for some reason, okay, let's say let's just imagine for a second, let's understand why this is different from just t itself. Because right now we're just setting it equal to t. But what if our list were like it was in the first example, and it wasn't generic, right? It just held I32s. Well, then we wouldn't have this, and we wouldn't have this, and it wouldn't be, generic. I mean, I'm breaking the code, but you see what I mean, right? So we couldn't refer to t, but we could still say our items are I32s. Like if this list were if this iterator was just always an iterator over I32s, we could say this is how we'd say it. Our item is I32s. And the definition of iterator is that the next method returns this option of self : item. So by defining that, we also lock ourselves into saying we return options of whatever is in the collection, in this case t, right? And it's really simple. In this case, the code is really simple to implement it because we've made it easy because we've decided that all we wanted to do was support this, and we don't need to do it twice. So we already wrote code that lets us iterate through it, basically. It's just pop. So all this next function does is it pops. And also we made it so that our into_iter takes ownership of the list. Here, into_iter, the method, takes self by value. So this means that in order to create an iterator, we have to literally give it our list. And then we can't refer to the list again, but we can at least use a for loop to go through it. So if I save this, it should work. Yes. And then if I do cargo test, I wonder if it works. It's very boring. It works. Okay. So yeah, what's going here? Yeah. Do you have a question?
What about ownership? So
yeah,
does it mean that what happens after iterator passed? So do we still have the list itself?
No, this makes sense. So this is a good question. So what I mean by ownership is when we call list.into_iter, because into_iter takes self by value, and because list is a fancier type, it isn't a copy. It's like fancier than an integer because it actually owns memory. This means that as soon as I call list.intoIter, I can no longer use the list. If I try to println the list or list.peek, right? I used to be able to peek into lists. Can't do it for a bunch of reasons. Interesting. Let's see. Okay, yeah, I made it, so list.peek didn't work because I was telling it to print it and it doesn't know how to print options, but now I told it print it in debug view, so that's not the problem. Now it's saying borrow of moved value. We moved list, we gave it to this method, and then this method created this thing which now owns it. It has it by value. And we lost our original copy. So the value of this is that this movement is actually implemented just as a copy of the raw bytes of our list. Our list is here, so all we had to do was copy the head, right? But in order to avoid double free problems, we invalidated the old list. So now we don't free the old list because that would be double freeing, because eventually when this intoIter goes out of scope, it will cause the lists destructor to run, and it'll free everything when it dies. So that's what ownership means. IntoIter is responsible for cleaning up lists memory. I forget which meetings you attended, but does that make sense? That was also kind of messy, but
yeah, I think so.
Okay, yeah. So this is annoying. And there is an option, I don't think we've implemented it quite yet, but there is an option to just say, okay, copy the list. We use the method clone, but it's not implemented here. But normally that can work. Like if the list was a string and we were trying to do this, we would do that. But more importantly, what we actually want to do for this kind of use case is we want to define a fancier form of iterator, which doesn't take ownership of the list, but just retains a reference into the list. Let me see if I missed anything here. No, I didn't really. Oh, I did want to say, this is just sort of a nice thing to say. Yeah, I already talked about tuple structs. The phrase for a tuple struct that looks like this is a new type wrapper, and this is a very common pattern for cases just like this, where it's like an iterator or something else, is like a type that has a different purpose, but it shares the same data as another type. The reason why we do this is because, well, we don't have to give this thing a name, right? Because it's a tuple struct. But the reason why we're doing this at all, instead of just doing type equals, like type intoIter equals list, is because type intoIter equals list just declares an alias. Whereas this creates a new type. And what that means is these two types are incompatible. I have to explicitly convert between them. And this is actually useful, especially if we're like making a game or whatever. You could imagine a situation where, or doing graphics more broadly, you can imagine a situation where we have like a tuple of 3 floats or whatever, right? And we can actually use that tuple as the underlying type for both colors and 3D points, right? And for colors, it's RGB. For 3D points, it's XYZ. But we actually want those to be separate types. So we might have an underlying like vec3 class, or struct, sorry, like pub struct vec3, and maybe this is also a tuple struct where it's just 3 floating point numbers. But we don't actually want to use vec3 very much except for the basic math operators. Whenever we're writing code, we want type safety where colors are different from vectors. So we have a pubstruct color, which is just a vec3, and we have a pubstruct point 3D, which is just a vec3. And these are incompatible, so I can't accidentally pass a color to a method that expects a point and vice versa. So that's sort of another motivation for this new type wrapper business. Hi, Harsh. I didn't notice you were here. But I'm going to take a brief break, and then I'm just going to try to motivate this. Okay. So yeah, this time we won't be able to rely on list giving us all the features we want, because list doesn't actually have a way to look at an item and then look at the next item, right? It only gives us a way to look at an item and then remove it and then look at the next item, right? So we...
Right.
What?
No, it's I'm talking to myself. So.
Oh, no worries. Oh, I just realized you have your video on and I wasn't able to look at it. 1 second. How do I... What am I doing? How do I, I hate Discord. I really
Correct position. Okay.
You do have your video on, right? Why can't I see it?
I do.
Okay, yeah. I don't know what's going on.
Sure.
How do I... there, I see you. Okay. Much better. Anyway, hello. Okay, yeah. So you've probably written an iterator in something like C++ before, where what we want to do is we want to hold a pointer to the current node, but that node might not exist. So we want that reference to be an option. And when we yield an element, we want to proceed to the current node's next node. So she doesn't actually talk about this, but there are a couple of options for how to hold a pointer in Rust. We've seen box and we've seen references. Which do you think we want and why? I can answer any questions that you have about references and boxes, because, you know.
I guess it doesn't depend what operator we want it to do. So if we want to just look through the list,
yeah,
we'll probably need a box. So that's
okay. So I think you've got them reversed, actually. So boxes own their contents. So if we had a box, then it would destroy its contents at the end. But we just want to look at it. So we want a reference. Like, references don't destroy the thing they point to when they go out of scope. And you can have another way of thinking about a box, the equivalent type to box in C++, which is a useful name, is a unique pointer. So a unique pointer in C++ is basically the same as a box. It's a self-freeing pointer. Like, you create it, it lives on the heap, and nothing else owns it initially. Nothing else even points to it initially. And then when it dies, it frees itself. So in this case, we don't want a box because we just want to look at the elements. Does that make sense?
Mm-hmm.
Yeah.
Yeah.
Yeah. So this definition looks pretty straightforward. We want an option of a node. It needs to be a node because we actually need to be able to traverse it, right? It can't just be a T. And then that's the last code I'm going to paste in here. But then I'm just going to say, okay. Actually, no. I'll just describe the issue here. Okay. So then we have this iter function for the list is just gonna, it's like our into iter function before. It just creates the iterator. Okay, so we take our head. Our head is a link, so it's an option of a node itself. We map it, which means this code runs in the sum case of that head. That head is an option of, it's an option of a box of a node, right? So the sum case runs, actually I'll just copy this because it'll be easier to do in my IDE. We already have errors, but whatever. This map takes the sum case, so it's the box of the node, right? And we say, okay, take a reference to it. And this actually is some fancy crap, because node is a box. So you might think like taking the address of a box would get me a reference to a box. But I think this is called deref coercion, where it automatically dereferences box and then just takes a reference to the underlying node. Because I think this code works. Like, I'm not seeing any red squigglies here. So I think, yeah, next has to be an option of a reference to a node, not an option of a reference to a box of a node. But this is fine. We have a reference to something that also has a box pointing to it, but that's actually not a problem. It's kind of crazy, but all that we have to do is we have to make sure that this reference disappears before the box. Because the box actually makes sure that the thing stays alive, right? The reference is just our view of it. And that's exactly what the issue we're actually running into is. We'll talk about this way more next time. But this is the issue that you almost always run into with references. Lifetimes. Lifetimes are the Rust language's language for talking about how long things last. In C, this is all up to you, right? In C, if I keep a pointer to something, I need to make sure that that thing exists for as long as I'm using this pointer, right?
Mm-hmm.
Rust will actually try to enforce this. So I'm not even going to go into this next code because that is important later, but she has the appropriate reaction to the lifetimes. Yes, they are scary. By the way, is the text here readable? I think it is, but...
Yeah.
Okay, good,
Yep.
good. But yeah, so then she says, okay, the nice thing is that when you get an error like this... a compiler error, it'll actually tell you, hey, you can ask Rust to explain it, and we can probably get an even better explanation. This error indicates that a lifetime is missing from a type. If it is an error inside a function signature, the problem may be with failing to adhere to the lifetime elision rules see below. Okay, don't worry about that. But it's not even inside a function signature. It's here. This is not inside a function, right? This is inside a struct. So this isn't... that didn't really clarify much. But it looks like we should add these tick A things. So then she just goes ahead and adds them. But at first I'm going to just try to explain what they're about. We've already seen variables in Rust, and basically every language has variables. We've also already seen these generic parameters, right? T. Sometimes we have to declare like T, like here, right? Before we can start talking about it. And that's because this is basically a variable for a type, right? This works for multiple types, right? A lifetime is a variable for how long something might last. So if I put exactly in the same place as I put the type parameter t here, I put this lifetime. Lifetimes always start with a tick. This is like I'm declaring a lifetime here. So this struct only works. What this is saying actually is this struct. To create one of these structs, you have to know that there is a lifetime that this struct... how does this work? there's a lifetime that this struct. No, there's a lifetime that outlives this struct. That makes sense. We need, in order to keep our iterator, we need the list that it's an iterator over to keep existing. Otherwise,
Right.
yeah. So this lifetime outlives this struct, and then we use this lifetime to say these references have this lifetime. So that means that our references in here point to something that is valid for this length of time in our code. You can think of it as like a vertical distance in our code. It starts somewhere where something's declared, here our list, then it ends where it's freed, usually like a closing curly brace or whatever. And this reference will refer to something that lasts that long. So in the end, we will, like, obviously we'll do this more next time, but we'll talk more about this concept. And we'll actually, sprinkle these lifetime things everywhere, basically, in our code, except not quite everywhere because Rust is sometimes smart enough to avoid it. And we'll be explaining to the compiler, okay, in order for this to work, the thing we refer to has to live at least as long as our iterator. And then the compiler is going to be able to check that, okay, if that's true, then you're good. Because then you're only using things that will exist, right? It'll look at our iterator code and it'll check that. And it'll say, okay, you're not using any lifetimes you haven't talked about. You said this struct needs to last this lifetime needs to last at least as long as this struct. And then you're using those references, and that's safe because by definition, that means that the thing that you're pointing to lasts long enough, right? And then separately, it can also check the usage of the iterator and say, this works and doesn't violate any rules. And it can make sure, but it'll also mean that if you misuse the iterator, like you try to keep the iterator around after you've dropped the list, Rust will yell at us about that. It'll say, you're violating these rules because you said that the iterator would last. No, you said that the list would last at least as long as the iterator, but then you got rid of the list while the iterator still borrowed it, and you can't do that. So this is how we explain to Rust the rules that we want to uphold, which are pretty simple in this case. The iterator refers to something in the list, so the list has to exist for as long as the iterator exists. We'll go more into the details, but I think I at least described the concept decently. And again, of course, this next bit in the chapter is particularly good at it. It is long, but it's a really clear example, pretty concise and really well written description of how exactly all this stuff works. So this is one of my favorite chapters, and one of my favorite passages in the book too. Anyway, that was, I think, a pretty good meeting. Do you have any more questions, just last minute stuff, or?
Yeah, mostly I'm a bit confused about lifetimes.
Yeah.
Still, I think I will just have to read about them.
Well, you can, but if you have a... Yeah, I mean, I guess, yeah. We'll talk about it more next time, I guess.
Okay. Yeah, okay.
But be thinking, even if you don't read about it, obviously, just be thinking of questions, because if you have any questions, I can definitely try to answer them at the start of the next thing. Or whenever. But yeah, so now we'll see how this recording worked out. I'm sure